Hi guys, welcome to the second lecture on the foundations of reach, grasp and manipulation. The focus of this lecture is going to be on understanding different ways of conceptualizing and understanding how functional movements are organized. Compared to previous lectures that we've had, we're going to get a little bit more theoretical than we have. Up until this point, I've tried to avoid spending too much time talking about different theories of motor control, and I've instead focused on telling you the facts that are known about the control of posture, mobility and manipulation within the framework of the systems theory. We've now reached a point in the class where it's important to bring in some additional theory. Remember, a theory is nothing more than a conceptual framework for organizing the facts. Our goal today is to understand different ways of conceptualizing how functional movements are organized. Our starting point for doing this is going to be looking at some evidence that reveals that movements are pre-planned before they're executed. We'll start by looking at a very classic experiment. This is Henry and Harrison 1961. This research gives us some insights into what is going into the organization of an action. In this experiment, you have the simple task of tripping the string in front of you by raising up your arm. To perform this task, you wait for the go signal, and when you hear that signal, you raise up your arm and trip the string. Now, you're expected to do this task unless you hear a stop signal. The red light coming on in front of you is going to be the stop signal. If the red light appears, you should stop immediately and stop your arm from tripping the string. The experiment unfolds in the following way. First, you get the go signal. After a certain amount of time, you'll see the movement being initiated. And then finally, you get the movement terminating after the string has been tripped. Movement initiation is the moment when you first start seeing the arm moving. At movement termination, you've tripped the string and stopped the motion of the arm. Let's look at what happens when we manipulate the timing of the stop signal. A fascinating finding in this research is that if the red light signal, the stop signal, is turned on after the go signal, but before you've started moving your arm, you will still start moving your arm. Not only that, you'll find that the entire arm movement still gets performed and the string still gets tripped. The only observable change that will occur with the arm movement is that it's going to be a little bit slower. This shows us that there is some kind of influence of having seen the stop signal. That even though the movement still occurred, the movement slowed down a little bit. Let's look at some other cases of different timings of the stop signal. If you receive the stop signal shortly before you're about to trip the string, then, unsurprisingly to most of us, there's no impact on the movement. You end up tripping the string and bringing your arm to a rest pretty much in the same way that would have occurred if the stop signal had never occurred. If we start shifting the stop signal back in time, we get the same result. If the stop signal is presented at any of the time points in this region that we've just highlighted here, there's no impact of the stop signal on the observed movement. You end up seeing the stop signal, but you're not able to stop yourself from tripping the string. This last case here that I just highlighted is a particularly interesting one. If you receive the stop signal shortly before you've initiated the movement, you're still not able to stop yourself from performing the movement. So even though you haven't started moving, you still end up performing the movement as in exactly the same way as if the stop signal had never appeared. There's no visible impact on how the movement actually looks. Let's think about the implications of the findings from this simple experiment. The participants in these studies were not able to stop their arm from moving in time to avoid tripping the string. A lesson for us in these results is that an action isn't just the movement that we see. An action is beginning to occur before the movement has even been initiated. This means that actions involve something that's taking place before you see any movement. and even before you see any force building up in the muscles. Findings like those of Henry and Harrison here have influenced the way that we think about the organization of action. They've led to the idea that action involves organizing a plan for action and then executing that plan. Today we'll be discussing the computational perspective on the organization of action. The computational perspective will introduce us to some computational language that's sometimes used to conceptualize the organization of action. From the computational perspective, the results of Henry and Harrison reveal that actions involve first loading a motor program and then executing that program. So you can see we're already starting to introduce some words from the computational perspective. The notion of program. The computational metaphor gives us the idea that once a program is loaded, it's organized to play out in full. Let's look at some more evidence that leads us to the conclusion that movements are pre-planned and then executed. We're going to be looking at another well-known study by Wadman. The study involves a very simple task again. You just have to rapidly extend your arm. You start with your elbow flexed, and when you're signaled to start moving, you quickly extend your elbow. You're also expected to decelerate the arm before it reaches full extension in order to stop yourself from damaging your joint. This research was designed to study the idea that the patterns of muscle activation that we see during a movement are pre-planned. To test this, the researchers formulated a hypothesis. And they formed their hypothesis based around what they would expect to see if muscle activations were not pre-planned. The researchers hypothesized that if the timing of muscle activations depended upon online sensory feedback of limb position and not pre-planning, then arresting the motion of the limb before it reaches the intended terminal position should eliminate the muscle activity associated with decelerating the limb. So, in this experiment, we're going to study the simple elbow extension movement in two different conditions. Either the movement is going to be blocked or it's not going to be blocked. In the blocking condition, the mechanical brace shown in blue here will engage so that when the participant starts to extend the arm, the brace will stop it from moving. In the unblocked condition, the brace is disengaged, allowing the arm to freely extend. So, in the blocked condition, you're going to be given the instruction to rapidly extend your limb. But unbeknownst to you, the mechanical contraption here is going to be locked in place so that it's physically impossible for you to actually extend your arm. Before we start thinking about the difference between the unblocked versus blocked conditions, I want you to pay attention to the patterns of muscle activation that we've got going on here. Look at the thick black lines in the top and bottom graphs. They show the patterns of muscle activation when the arm is unblocked. So, just the patterns you would expect just from extending your arm and then decelerating it to avoid damaging the limb. In the top graph, we see the triceps activation pattern. In order to accelerate the limb, we're going to need triceps recruitment. The first burst of activity that we can see in the graph is going to give us an initial burst of forearm extension. Now, if we look at the graph of biceps activation at the bottom, we see that a burst of biceps activation occurs immediately after the triceps activation. This biceps activation is going to decelerate the limb and stop us slamming into the end range of the elbow joint. And lastly, we see a second burst of activity in the triceps in the top graph. This triceps activation is involved in stabilizing the limb around its end position. When we look at multiple recordings of this simple action across multiple people and across multiple recordings of the same person, we reliably see this triple burst characteristic activation pattern. This pattern of muscle activation is essential for a functional movement to occur. It involves the accelerating of the arm, the decelerating of the arm, and the stabilization of the arm at the end of the range of motion. Okay, now let's focus on the interesting part. If you start to compare the thick black lines in the graphs that represent the muscle activation patterns in the unblocked condition to the thinner grey lines that represent the muscle activation patterns in the blocked condition, you'll notice that they both have the same characteristic triple burst pattern. What we're finding here then is that the triple burst pattern is present in the blocked motion trials, where the arm doesn't even move at all. We see a situation here when even though you're not actually producing a movement, you still see the characteristic sequencing of muscle activations. So, what's the conclusion we want to draw here? There appears to be some kind of pre-generated plan that's prescribing the recruitment and timing of muscles. And even if you put something in the way of that plan unfolding, once that plan has been put into motion, you can't stop it from unfolding. Let's look at one final bit of evidence that supports the idea that movements are pre-planned and then executed. Here we have a person grasping a cube and then lifting up the cube. In this task we can see pre-planning in action. If a person knows the weight of the object, then the force that's applied to grip the object is adapted so that only the force that's needed will get applied. A person can know the weight of the object if that object has been lifted up before, or if it's a familiar type of object, for example, if it's an apple, an orange, or a cup of coffee. Knowledge of the required grip force is going to be used to plan the grasp and the lift. So let's have a look at some data that's associated with this, performing this particular task. In the top graph, we see a time series of the load force. This shows the forces that are acting to counteract the forces due to gravity acting on the object, as well as the forces due to the inertia of the object as it's moved. These forces largely determine the grip forces that will be required in order for the object not to slip out of the hands as it's lifted up. In the graph, you can see that we have different lines for objects with different weights. The greater the weight of the object, the greater the load forces that are associated. In the middle graph, we see the measurements of the grip force that's being applied. Lastly, in the graph at the bottom, we see a time series of the vertical position of the object as it's been lifted up. So what are we seeing in these graphs? If you visually compare the load force graph to the grip force graph, you'll notice that the grip force is leading the load force, that you start to see an increase in grip force before you see an increase in load force. In other words, the participants are establishing a firm grip before they attempt to start pulling up on the object. We're also seeing that greater grip forces are being applied to heavier objects. So, here we see grip force leading load force. Okay, we've now looked at a few different studies that give us evidence that movements are planned and then executed. In light of this evidence, let's start to think about how we might conceptualize what we've just learned. Before we get into some of the more modern theories, let's lay some foundations of how the ideas of planning and execution have been thought about historically. The 19th century view of how movements are planned and executed was inspired by the discovery of the topographic map of the primary motor cortex. The classical work of Penfield and of Fritz and Heidsieck demonstrated that stimulation of different regions in the primary motor cortex evokes specific actions. Importantly, the primary motor cortex appears to map out the parts of the body, such that stimulation of nearby regions in this cortex will evoke actions in regions of the body that are close to each other. The lesson that many have drawn from findings like this one is that actions are organized in higher centers of the brain, in the cortex. In other words, actions are organized through some form of central executive system. Let's take a look at a cartoonish schematic that's capturing the ideas of the time. So we have this idea of a central executive in this little cartoon drawing. The central executive is represented by a blue ghost, a ghost in the machine. This central executive is going to be reading plans for action from a library of movements. It's going to retrieve a plan from the library, and it's going to play out that tune on the cortical keyboard. The analogy of the cortical keyboard is capturing the discovery of the topographic map of the primary motor cortex. The tune played out on the cortical keyboard is going to cause another tune to be played out on the spinal keyboard. Okay, let's unpack these ideas of the nature of action organization a little bit. The central idea here is that functional movement is some kind of a complex concerto of instructions. We have the idea that we have a library of complex concertos stored in memory. We have the idea here that for every movement that we could possibly want to perform, that there's going to be a score for it. Each score is written in a book stored in memory somewhere. And if we want to perform a particular movement, we're going to pull that movement from the library and then play it. We've got the idea here that a score is going to be retrieved from memory and played by the central executive. We also have the idea that the score is going to contain commands that are instructions to individual alpha motor neurons. Before we move on to the next slide, I want you to pause and consider the implications of this kind of 19th century view. Realize that many of the aspects in this model are actually reflected in modern theories. This historical conceptualization is also useful because it reveals some of the key challenges to be faced by any modern theory. A key challenge for any modern theory is going to be answering the question, what do plans actually look like? In a historical model, movement plans are scores written in library books, and these library books are containing instructions for the commands to be sent to every single alpha motor neuron. Furthermore, we're going to have a plan for every single movement in our library. The challenge, if you're intuiting it already, is that how could you have a memory system that could contain and organize the absolutely vast amount of information necessary to produce the rich array of movements that we're actually able to produce in this level of detail? And we'll be exploring this idea on the next slide. The challenge we were just discussing has been called the degrees of freedom problem. The degrees of freedom problem was first described by a Russian physiologist named Nikolai Bernstein. Bernstein looked at the action system and realized the challenges posed by having a system that had a very large number of controllable units. So, if we look at motor units that we were discussing on the previous slide, we have somewhere in the region of 10 to the power of 6 to 10 to the power of 7 motor units in the human body. Faced with this daunting number of controllable units, the glaring question for us is, how could you possibly have a central executive that could regulate so many individual units? At this juncture, you might turn around and say, well, maybe motor units aren't what's actually controlled. Maybe muscles are controlled. If we're controlling muscles, then we need to account for about 10 to the power 3 muscles. We might turn around again and say, maybe it's not muscles that are controlled. Maybe the central executive system is commanding or controlling joint positions. In that case, we have 10 to the power of 2 joints. In each of these cases, we have a fundamental challenge in understanding how you could organize or pre-organize actions in the central nervous system. For Bernstein, this is one of the most fundamental challenges for a theory of motor control. You might not be surprised to learn that the modern concept of synergies that we've discussed earlier in the semester is motivated by Bernstein's discussion of the degrees of freedom problem. You're probably used to the phrase degrees of freedom referring to joint motion specifically. Bernstein here is using the term more broadly to refer to controllable elements in the action system. So Bernstein is talking about motor units as potentially being degrees of freedom. We're talking about muscles as potentially being degrees of freedom, and more, as you're more familiar with, as joints potentially being controllable degrees of freedom. So to sum up, for Bernstein, the fundamental challenge for a theory of motor control is to understand how the many degrees of freedom of the body are harnessed in a way that yields functional actions, while involving the central executive system as little as possible. Now, when we're talking about functional actions here, we're talking about movements that are adapted to the context of constraints. So given the challenge posed by the degrees of freedom problem, how are functional movements organized? Bernstein suggested that the degrees of freedom problem could at least partially be solved by uncovering organizing principles that act to compress the degrees of freedom. When we look across modern motor control theories and throughout the literature, we come across a number of organizing principles that have been proposed. These organizing principles mean that the higher centers of the central nervous system do not need to individually regulate all of the individual components of the motor system. Organizing principles, then, provide key concepts for understanding how the burden of control on a central executive can be reduced. So, let's have a look at some different organizing principles. The concept of synergies is the idea that the action system organizes functional groupings of muscles rather than attempting to control specific muscles or specific motor units. Other principles that we see throughout the literature include biomechanical constraints, Feldman's lambda theory, motor programs, optimizations, systems parameters, the one-third power law, and principles governing reflex combinations. Some of these we're going to touch on in this lecture today, but I've got this list for you here just so you can get an appreciation that there's a pretty rich literature that is looking for the principles that allow us to understand how the degrees of freedom problem gets solved by the nervous system. One way we can get insight into the question how are functional movements organized is to look at the functional organization of the central nervous system. A long-standing hypothesis about the function of the primary motor cortex has been that the primary motor cortex is involved in the control of specific muscles. Neurophysiological investigations into the function of the primary motor cortex has revealed a much richer and much more complex story than originally thought. When researchers go in and stimulate different neurons within the primary motor cortex, they found that it's not just specific muscles that end up being activated. Instead, specific neurons within the primary motor cortex are associated with the initiation of functional actions. What do I mean by this? Rather than seeing a specific muscle being activated when we stimulate a particular neuron in the primary motor cortex, we can see particular groups of muscles being activated. When we go in and activate a different part of the primary motor cortex, we can see that stimulation mapping onto particular directions or velocities of movements of the hand through space. When we go in and activate yet another part of the primary motor cortex, we can see that stimulation bringing about particular changes in joint angles. And most elaborately, we can see that stimulation of some neurons in the primary motor cortex can lead to the production of particular types of functional actions in space. This last finding here is particularly interesting. In the diagram, each box shows an action that results from stimulating a particular area in the primary motor cortex. In box A, for example, we see that there's a particular area in the primary motor cortex that, when stimulated, will lead the monkey to move its hand to its mouth. The dotted lines in this figure are the different hand trajectories that follow from the hand starting in different places. What we see then is that it doesn't matter where the hand starts. Whenever you stimulate a specific set of cells in the primary motor cortex, you will see the hand move to the mouth. All of these different movements towards the mouth are equifinal. We use the word equifinal because all of these movements produce the same end result of the hand being brought to the mouth. In this particular case, we're seeing that the primary motor cortex is responsible for a functional feeding motion. It is triggering the functional action of bringing the hand to the mouth. It doesn't matter where the arm starts. The different hand motion paths involve different joint motion combinations and different muscles being utilized. This tells us that this part of the primary motor cortex is not controlling specific muscles or specific joints. Instead, it's controlling actions. Here's one of the schematics we looked at when we were studying mobility. This schematic illustrates the idea that synergies are higher-level organizations that act to bring together subsets of muscles into functional units. What we're learning here is part of the story regarding how the central nervous system is organized so as to solve Bernstein's degrees of freedom problem. Let's have a look at some evidence for the existence of synergies in reaching and grasping. The research in this area shows us that reach and grasp are functionally coupled. It shows us that reach and grasp are not independent of each other, and that when you see changes in one, that you'll see changes in the other. It shows us that reach and grasp are functionally fitted together in a particular way. The first piece of evidence suggesting that reach and grasp are functionally coupled comes from observations that maximum grasp apertures reliably occur at 75% to 80% of reaching movement time. This particular proportion, where maximum grasp aperture is occurring at around 75% of the movement time, is invariant across multiple variations in the specifics of the movement. The particular ratio is unchanged if we have a reach-grasp motion that takes more or less time. It's unchanged if we have a slower reach and grasp or a faster reach and grasp movement. And we can change the initial finger postures to make the fingers closer together or further apart. By doing this, we might expect that this would change the timing of the grasp. But no matter what we do, we end up seeing the maximum grasp aperture, as we're reaching forward, to be occurring at a fixed proportion of the time throughout the reach. So what's this telling us? It's telling us that the timing of the grasp is tied to the timing of the reach. The second piece of evidence that reach and grasp are functionally coupled can be found in findings that reach and grasp component actions adaptively covary. You'll remember the phrase adaptive covariation from earlier in the semester when we were looking at the uncontrolled manifold approach. We saw adaptive trade-offs between the elemental variables in a synergy. This allowed for flexible combinations of forces in order to produce the invariant functional outcomes that we were observing. In the context of reaching and grasping, if an object to be grasped is displaced mid-reach, that is, if we perturb the reach by moving the object either nearer or further away mid-reach, then what do we see? What we see is that the perturbation to reach is also a perturbation to grasp, and that the grasp is also affected. Even though we're changing the distance that the arm needs to travel, and we're not actually changing the width of the grip aperture that the fingers need to move apart, you end up seeing the grasp also being affected. This suggests that the two are tied together in some way, and that they're going to adaptively covary with respect to each other. We can look at adaptive covariation of reach and grasp in a different way. We can change the size of the object being grasped mid-reach. In this case, you start reaching towards an object, and it suddenly either gets bigger or smaller. What we're doing here is perturbing the grasp. The question now becomes, are the kinematics of the reach also going to be affected? As you've probably anticipated, when you do this, you see changes to the kinematics of the reach. These studies clearly demonstrate that reach and grasp are functionally coupled. This is generally consistent with the idea of reach-grasp synergies. Today, we're going to spend some time looking at the computational perspective on the functional organization of human movement. To place the computational theory in its appropriate historical context, it's important to realize that throughout history, many of the major theories of the organization of human movement took inspiration from the technologies of their time. One such theory was Descartes' hydraulic theory. We're not so much interested in the specifics of Descartes' hydraulic theory. Instead, Descartes' main legacy in modern theories of motor control is the idea that humans and animals can be understood as being complex machines. So we've been talking about the challenge of understanding how functional movements are organised. Today we're going to spend some time looking at the computational perspective on how functional movements are organised. To place the computational theory in its appropriate historical context, it's important to realise that throughout history, many of the major theories of the organisation of human and animal movements have taken inspiration from the technologies of their time. The computational theory is not an exception to this. One such theory is Descartes' hydraulic model. We're not so much interested in the specifics of Descartes' hydraulic theory. Instead, Descartes' main legacy within modern theories of motor control is the fundamental idea that humans and animals can be understood as being complex machines. Descartes got this idea by going to the technology expos of his time and getting inspiration from the mechanical wonders on display. Here we see some of the technologies that have inspired the computational theory. At the top we see a diagram of a universal Turing machine. This is one of the earliest major innovations in computational theory. To the right of that, we see some computing systems from the 1960s. And below that we see a punch card which was used to program 1960s and 1970s IBM computers. When we look at the punch card, we see that in order to send instructions to the computer, you had to punch holes into the punch card at different points. The holes specified the particular ordering of instructions to the computer. Down at the bottom, we see a robot that we've met before. This is Asimo. This is a robot whose movements are computationally programmed, and where all of the specifics of the movement are largely being dictated by lines of code. Lastly, the man that we have depicted here is Herb Simon. Simon proposed the artificial intelligence theory. This particular approach explored the idea that humans are symbolic information manipulation systems. And the ideas and insights of Herb Simon have played a large role in modern computational theories of human motor control. We've just been looking at some old inventions that have inspired the ways of understanding human motor control. What then are the more recent innovations that are and how are they inspiring us to understand human motor control in new ways? So here we're seeing some of the cutting edge of modern robotics. This robot, which Boston Dynamics calls Spot, is able to expertly regulate its posture. It's able to adaptively move its body through complex environments, and it's able to manipulate objects. So here we have another robot from Boston Dynamics called Atlas. We can see that Atlas produces remarkably fluid motions. We can also see that not every part of the movement that's being produced here is being prescribed ahead of time. In other words, what we're seeing is that Atlas's movements are adapting themselves to the forces in the environment. This is quite different from the type of control that we see being used in the Asimo robot. The principles that are being applied here we're going to encounter right at the end of today's lecture. Let's start looking at the computational perspective. The simplest part of the computational perspective is going to be the concept of a motor program. To understand the concept of the motor program, let's look at some more research. So in this research, we've got a simple task. The task begins when you press and hold the red button, and when you do this, it's going to start the purple hand on the clock face moving around. While you're holding the button down, the hand will sweep around at a rate of about 1 cycle per second. The next part of the task is to release the button when the purple hand gets to the 8 o'clock position. The goal then is to end up with the clock hand pointing towards 8. The next part of the task is the most interesting part. On some trials, the sweeping hand is going to randomly stop before it reaches 8. For example, the hand might be sweeping around and it might randomly stop at the 3 position. If the hand does stop early, your task is to make sure that you don't release the button. This means, to do the task correctly, you should not release the button when it reaches 8. Given that this research was completed in the 1960s, at the height of the Cold War, and 2 years before the Cuban Missile Crisis, you can understand some of the historical context for wondering how effective people can be at pressing or not releasing buttons. So let's look at the results of this study. Here we see the pattern of results. On the x-axis here, we've got the amount of time before the hand reaches 8 that the hand is going to stop moving. So, at 0 milliseconds here, this means that the hand is going to stop moving when it's exactly at 8 o'clock. At 100 milliseconds here, this means that the hand is going to freeze in place when it reaches around about 7. At 450 milliseconds here, this means that the hand is going to freeze in place when it gets to 3. So again, your goal is to release the button when it reaches 8, unless the hand freezes in place. So the clock will start going around, and on this particular condition here, it's going to freeze in place when it reaches 3. And when it freezes in place, your job is to not release the button when it reaches the 8 o'clock position. So on the y-axis here, we've got the probability of inhibiting the planned response. If it's 100, it means that there's a 100% chance that you're going to be able to inhibit the planned response, that you're going to 100% of the time be able to stop yourself from releasing the button. 0, on the other hand, means that there's no chance, and the 0.5 means that there's a 50% chance. So, as we get closer to the time of release, what we see is that you're no longer able to inhibit the planned response of releasing the button. So, up here, what we can see is that you can stop yourself releasing the button, and down here we see that you can't stop yourself from releasing the button. So what's the takeaway from this particular research study? The takeaway here is that we can interpret these results to suggest that there's a motor program that's being loaded and then executed. And that as soon as the process begins, as soon as you start loading this program, it's not easy to interrupt this program. At the heart of the computational approach is the idea that motor control depends upon internal computational processes. Given this idea, we can come up with a very simple way of conceptualizing and studying the organization of motor control. This approach has been called the black box approach. In this approach, we assume that there is some input that triggers the intention to perform an action, and that there's some output that represents the performance of the action. And also that there's some internal computational process that's operating to organize the planning and execution of the action. The simple idea behind this approach is that if we measure the amount of time between the input and the output, that we can learn something about the hypothesized internal computational processes. For example, we could look at the simple task of asking someone to tap their finger on the table when they see a red light come on in front of them. So the input here would be the red light signal, and the output would be the tap. We can measure the amount of time between the light coming on and the tap occurring. So between the input and the output, we assume that there's some kind of internal computations going on. This is called the black box approach because we're not able to directly measure the hypothesized computations themselves. We're just able to make inferences about those processes based upon how much time is elapsing between input and output. So let's have a look at this kind of logic in action by considering the research of Henry and Rogers. Henry and Rogers proposed the response complexity effect. They proposed that more complicated movements should take more time to initiate. In other words, they proposed that more complicated movements should have greater reaction times. Reaction time simply refers to the amount of time that elapses before we can see an observed reaction to a stimulus. So, we can measure the reaction time for various types of action. For example, for a single joint arm movement, we can measure the amount of time it takes for the arm to start moving after a go signal of some kind. Henry and Rogers observed that the reaction time for a single joint arm movement was reliably less than that observed for a coordinated arm movement, like a reaching movement that would require both a shoulder movement and an elbow movement. Moreover, they found that the reaction time for a coordinated arm movement was reliably less than that observed for initiating a movement that required coordinating the actions of the eyes, head, body, and arm. In each of these cases, we're talking about the amount of time it takes for the initiation of the movement. We're not looking at how long it takes to perform the actual movement itself. The finding here, then, is that the amount of time leading up to when the movement is initiated is greater for more complex movements. So how do we interpret these results? Henry and Rogers proposed that more complex movements are more computationally demanding. They proposed that more complex movements are going to require more operations, and they're going to involve harder operations, and that they're therefore going to take a longer amount of time to compute. A valuable part of any theory of motor control is the ability to explain why one person is more or less effective at performing a given task than another person. The computational perspective gives us a simple way of conceptualizing performance errors. Richard Schmidt, one of the original developers of the notion of motor programs, proposed that there are two key types of error that occur in the performance of a particular movement: selection error and execution error. When we talk about a selection error, we're talking about the wrong motor program being chosen. We have a particular motor challenge that we're being faced with, and we happen to select the wrong program for the task. A couple of slides ago, we looked at an experiment by Slater-Hamill. We learnt that once a motor program was loaded, that it is difficult to interrupt the execution of that program. Because of this, there's going to be big consequences for this kind of error. If the wrong program has been selected, then that wrong program may end up having to be played out in full before any feedback is generated about the error in program selection. Schmidt proposes that only once the wrong program has been played out can a new program be loaded and executed. In the case of an execution error, we have the right program selected and the right program being played out, but the effective execution of that program is going to be disrupted by internal or external noise. Put more simply, some kind of perturbation is going to disrupt the execution of the program. From the perspective of motor programming theory, an execution error can be corrected far more quickly than a selection error, because the correction is not going to require the loading of a new program. With a selection error, you still have the same program, but you just need to adjust the details of the program in order to deal with the source of error. These concepts have implications for understanding the kinds of errors that are performed, and the amount of time that's needed to correct certain errors. A selection error is going to take a much greater amount of time to correct than an execution error. Now that we've introduced the concept of a motor program, I want to talk to you about some of the problems with this particular concept. So, what are the problems with using the concept of motor programs as the basis of a theory of functional movement? The main problem with the basic concept of a motor program is the storage problem. The storage problem is related to the idea of memory saturation, the idea that memory could become full up. If we think back to our analogy to the 19th century view of motor control, we saw a library full of books, and these books effectively had motor programs in them. The books had scores that were describing the specifics of the movement. What we were talking about here with the storage problem is that if we had lots and lots of motor programs, at some point the library would get full up. The theory of functional movement that we care about here is a theory that's going to help us understand how movements can be reliably performed in real-world contexts. The theory we desire is a theory that can explain how movements are skillfully adapted to the demands of the real-world situations and real-world contexts. The problem with motor programs, then, is if we have programs and subprograms for every respective movement and every movement components, and we also have multiple variants of the programs that are tailored to the specifics of every possible situation, then we'll end up with an unfathomably large number of programs. Understanding what we mean by a massive number of programs becomes very clear when we begin to think about the number of variants of actions that would be needed to tailor an action to every possible situation that it's performed in. Think about the task of throwing a ball using an underhand throw. The variants of this act could include throwing a ball when the lights are slightly turned down, when the lights are slightly dimmer, when the ball is slightly lighter or slightly heavier, throwing an apple or throwing an orange. Other variants could be throwing that apple or orange 2 feet away or 2.5 feet away, and so on. According to the initial first developed theory of motor programs, all of these subtle variants would require separate motor programs to be stored in memory. So next, we have the novelty problem. If all movements are pre-structured, then where does the structure for a new and novel movement come from? If we have a vast amount of experience throwing an apple, and then along comes the novel situation of trying to throw an orange that's heavier than the apple, how do we end up having a plan for doing this? How do you end up actually adapting yourself and not having to come up with a completely new plan for every single new situation? The challenges posed by the storage and novelty problems motivated a major advance in the motor program theory. Motivated by the storage and novelty problems, Smith proposed the idea of generalized motor programs. A generalized motor program is an abstract or general action plan. With a generalized motor program, we have many movements forming a particular class of movements. And all of the movements in this class are going to be run by the same program. This means that we can have many different movements all in the same class, all being run by the same general program. This means that we're going to get far fewer programs, and we've made a big dent in the storage problem. In order to pull this off, we're going to need some new concepts. Smith proposes that a generalized motor program is composed of invariant characteristics and parameters, and we'll talk about parameters in a second. The concept of invariant characteristics is used to define how movements fall into a particular class of movements. For example, you might have a movement that has a particular relative timing to it, such that different aspects of the movement are occurring at different proportional times. Think about when we were looking at the reach-grasp synergy. We were seeing that the peak grasp occurs at a particular proportion of time compared to the reach. So it doesn't matter if we reach a certain distance or change the size of the object, there are many different types of reaches and grasps that can be performed, and they're all going to have the same relative timing. The relative timing of reaching and grasping is one example of an invariant characteristic. You also see this constraint of relative timing existing in reactive balance strategies and in the organization of walking and running movement patterns. We also see the relative timing existing in the organization of handwriting, and we'll elaborate on that particular example in the next slide. Another invariant characteristic is the order of events. So you have a particular movement, let's say a reach and grasp, that requires a reach and then a grasp. Thinking about the order of events, we can also think about the everyday example of creating buttered toast. To create buttered toast, you require a very specific order of events. You have to put the bread in the toaster, and once the bread is toasted, you can then put the butter on the toast. You can't put the butter on the toast and then put it in the toaster. So there's a particular ordering to the event that's required and is going to remain unchanged. Another invariant characteristic that you see in various types of movement is a particular balance of forces existing across the various components. So that gives us some examples of invariant characteristics. Now that we've discussed them, let's move on to the concept of parameters. Parameters are the means of tailoring generalized motor programs to new contexts. This is how we're going to solve the novelty problem. Imagine that you have a generalized motor program for throwing, but you've never thrown a ball to a target that's 2.5 feet away. What you can do then is modify the duration, the force, and the particular muscles that are going to be recruited in order to adapt the parameters of that generalized motor program to the demands of the novel context that you're experiencing for the first time. One of the interesting notions that comes out of the generalized motor program theory is generality. The issue of generality concerns the challenge of how it's possible to have learnt a particular skill in a way that allows that skill to generalize across multiple contexts. Let's look at a simple example. If I learn to draw the letter A in a classroom, it turns out that I've learned to draw many variants of the letter A. Let's look at some examples of this. Here we have a handwritten letter A. Here we have a letter A painted on the side of a wall. We see some different letter A's written on blackboards, and on the left we see a gigantic letter A written on a beach. Drawing all of these A's involves very different patterns of movement that use very different muscles and employ very different forces. From the perspective of a generalized motor program, these varied movement patterns can have the same underlying basis. By virtue of learning how to write the letter A, you've developed the ability to apply what you've learned across a large variety of contexts. The reason for this is that the performance of writing a letter A is going to involve the same relative timing across the writing of all of these different types of A. The timing is going to be invariant over all of the different scales of action that are involved here. So here we have the invariant characteristic in terms of involving the same relative timing. The recruitment of different muscles is going to be the parameterization of the generalized motor program. We're going to move on from talking about motor programs to thinking about the kinds of computations that the central nervous system might need to perform in order to organize a movement. The ideas I'm going to be discussing over the next few slides are drawn in large part from the field of robotics. In order to make Asimo make a particular movement, various transformations need to be computed. To move Asimo's hand, or end effector, to use the more technical term, we need to create a movement that changes the position of the hand P over time T. In order to get the end effector to change its position over time, we're going to need to have a particular change in the joint angles. To do this, we need to organize a particular combination of changes in joint angle that will produce the change in position that we desire. In order to produce the joint angle changes we require, we need to organize the patterns of torques that will produce those particular changes in joint angles. So what we're looking at here is the kinds of transformations that Asimo needs to deal with. So we have torques that are going to need to be programmed into the torque motors in order to produce changes in joint angles that will produce changes in end effector position. I hope you're beginning to see the challenges here. For understanding human movement control, we additionally need to understand what kinds of changes in muscle states are needed. We need to identify the patterns of muscle activation that will produce the patterns of joint torques we need, that will in turn produce the changes in joint angles we need, that will in turn produce the changes in end effector position that we need. From the computational perspective, we've got some very serious computational challenges here. This analysis that we've got here suggests that we have to compute a large variety of transformations, and we will have to be able to effectively move backwards and forwards across these different levels of description in order to produce a particular movement. Our diagram on the bottom of the screen depicts all of the variables that we're considering here. We've got the different joints, the shoulder joint, the elbow joint, and the wrist joint, and we also have the end effector. In this diagram, the end effector is the tip of the finger. We've got the torque at the shoulder, the torque at the elbow, and the torque at the wrist, and we've got the angles of the shoulder, the elbow, and the wrist. Pay attention to the notation that we're using here, because it's going to be useful in a minute. The symbol theta is being used for joint angles, the letter T is being used for the torques, and the letter P is being used for the position of the fingers. With this simple framework laid out, I want to review the transformations that you're most likely to come across in the literature. The simplest transformation that we can think of in this system is referred to as a direct kinematics transformation. The reason that this is a simple transformation is because if you tell me what every joint angle should be, then there's only going to be one position of the fingers that could possibly result. So calculating direct kinematics means taking measurements of the joint angles and transforming those joint angles into a finger position. Next, we have the inverse kinematics transformation. As you can intuit from its name, it's the reverse of the direct kinematics transformation. Given a particular change in position of the fingertips, what is the joint angle? What's the set of joint angles which will have produced that particular movement? As we'll discuss on the next slide, inverse kinematics is a much more difficult transformation to compute. This is because the same position of the fingers can be produced in very many different ways by creating different combinations of joint angles. Rather than looking at kinematics, we can look at dynamics. In the case of dynamics, we're looking at torques rather than angles. In the case of direct dynamics, we're looking at the transformation that takes the torques at the shoulder, the elbow, and the wrist, and based upon those torques calculates where the finger is in space and how it should be moving. In the case of inverse dynamics, the challenge is to start with the particular position and motion of the fingertip and then work out what's the particular combination of torques that would be needed in order to produce that particular position and motion. So let's relate this to the challenge of planning a human movement. Imagine you're looking at an object on the desk in front of you. You're planning to reach towards it, and you can visually perceive the spatial relationship between your hand and the object. You can also visualize the reaching trajectory that your hand would need to take in order to get to the object. Given the desired path through space that your hand wants to take, how do you come up with a plan? How do you come up with a program of the required kinetics? How do you come up with a plan of the particular combination of torques that should be applied at your shoulder, at your elbow, and at your wrist that would be needed to get your hand to the target? I mentioned that computing inverse kinematics is more challenging than computing direct kinematics. The reason for this is referred to as the inverse kinematics problem. Here we have our simplified representation of the arm again. To recap, in the direct kinematics transformation, if you give me a shoulder angle, an elbow angle, and a wrist angle, I can easily compute the one and only finger position that must result from that combination. Based upon the kinds of calculations that we were doing in the biomechanics class last semester, if you gave me all of these angles, I can know where the finger must be located in space. In an inverse kinematics transformation, if you give me the position of the finger in space, and you want to know, given that position of the finger, what the joint angles of the shoulder, the elbow and the wrist should be, we encounter a problem. The problem is that there's very many combinations of shoulder, elbow and wrist angle that could have produced the particular finger position that you gave me. What we're describing here is known as the inverse kinematics problem. Here you can see the finger is pointing at the exact same location in space in all four of these different pictures. In each of these pictures, we can see that there are multiple configurations of the joints that are producing the exact same finger position. What does this mean? This means that if you give me a particular finger position, that there are many combinations of joint angles that could have produced it. Here we see a chicken solving the inverse kinematics problem. The chicken is controlling the position of its head in space. We can see that the chicken is faced with the motor control challenge of maintaining a constant position, and is coming up with a combination of body, neck and head motions that produce the stable position of its head. Pause for a moment to think about the wonder of this chicken. At this point, you should be realizing that if you gave me the challenge of trying to calculate what joint angles or changes in joint angles will be necessary to produce a particular position of the finger or movement of the finger, that it's just not straightforwardly computable. In summary, if I am programming a finger movement, the question is, how can I decide which of the many possible combinations of changing the shoulder angle, changing the elbow angle, and changing the wrist angle should be computed? So this is the inverse kinematics problem. This leads us to the notion of optimization principles. Optimization principles provide one means of dealing with the inverse kinematics problem. Basically, if the inverse kinematics problem is the challenge of deciding which of the many possible combinations of shoulder, elbow and wrist angle will create the position I desire, then the solution to this challenge, based upon optimization principles, is to choose the particular combination of shoulder, elbow and wrist angles that is optimal in some way. The idea of optimization is that we have a system that's organized to minimize some particular type of cost function. Earlier in the semester, we saw that a comfortable walking speed is associated with certain cost minimizations. At the preferred comfortable walking speed, you see head movements are being minimized, and we saw energetic cost being minimized. A wide variety of hypothesized optimization principles has been investigated in the literature. Investigated optimization principles include minimizing peak acceleration in a movement, minimizing the amount of time it takes to perform a particular movement, minimizing the peak velocity or the impulse in a movement, minimizing jerk, and minimizing energy. To summarize, what's being proposed here is a solution to the inverse kinematics problem. A way of working out what particular combination of joint angles should be used in order to produce the position of the end effector. The solution offered here is to identify the combination of joint angles that are optimized in some particular way. For example, using the minimization of energy optimization, we would choose those particular combinations of changing shoulder angle, elbow angle, and wrist angle that would have the least amount of energy involved in performing them. Now let's look at some research that suggests human movements are in part organized through optimization principles. I'm going to talk about some research by Neville Hogan. Hogan proposed that human movements are optimized via the minimum jerk principle. Hogan proposed that movements are organized so as to minimize the physical property of jerk. I'm guessing many of you haven't heard of jerk before. Jerk is a physical quantity, and it represents a particular kinematic property of movement. You all understand what I mean when I talk about movement velocity. Movement velocity is the change in position over time. You all understand what I mean when I talk about movement acceleration. Acceleration is the rate of change of velocity over time. Jerk is the change of acceleration over time. We go from position to velocity to acceleration, and then we go to jerk. A random factoid, after jerk, we end up going to snap, then crackle, then pop. So these are higher and higher orders of rates of change. So what's the idea here? The idea here is that the central nervous system is going to organize movements in a way that minimize the sum of squared jerk along its trajectory. This is the formula for doing this. You don't need to remember this formula for the exam. You just need to remember the concept. When jerk is minimized in a reaching trajectory, a characteristic or invariant pattern of end effector motion is observed. Specifically, a bell-shaped tangential velocity profile of the end effector movement is observed. An example of a bell-shaped velocity profile for reaching is shown on the right. In a reaching movement, initially the velocity of the hand movement is 0, then it increases up to a peak velocity, and then it decreases back to 0. The minimum jerk principle is interesting because it provides a basis for explaining why the movement trajectories look the way that they do. Here we see the movement profiles that would be predicted if different particular variables were optimized. The triangle-shaped profile shows the changes of velocity we would expect to see in a reaching movement if a reaching movement was optimized in order to minimize the peak in acceleration. We also see the curves for minimizing peak velocity, minimizing energy, and for maintaining a constant stiffness. Minimizing jerk seems to be the best explanation of the velocity profiles that are characterizing human reaches. For reaching movements, the minimum jerk principle predicts the straight line hand trajectories that we see, the bell-shaped velocity profiles that we see, and we're going to be talking about these bell-shaped velocity profiles more in a second. It also predicts the slight curvature that we see in human hand reaching trajectories. So, why are human movements organized in a way that minimizes jerk? A movement that has a high level of jerk to it will require large torques and forces. It's also going to require very rapid changes in torques and forces. These kinds of changes are potentially destructive and are going to promote tissue failure and tissue degeneration. So there's some basic functional reasons why we might have a movement system that's organized in this particular way, in a way that minimizes the squared jerk along its trajectory. Next, I want to move on to another concept from the computational approach to motor control. In many computational approaches, internal models are hypothesized to be involved in trajectory planning and control. Two main types of internal models have been proposed: inverse models and forward models. In the case of inverse models, we're talking about computing the dynamics that are required to achieve a particular set of spatial coordinates. If I want to move my hand through space to reach my coffee mug sitting next to me, which I'm probably going to be doing in a second, what are the dynamics, what are the particular torques or patterns of muscle activations that are required in order to produce that movement? Forward models are hypothetical mechanisms for predicting the effects of internal and external dynamics in order to properly adapt movements. Last lecture, we talked about a waiter holding a tray of drinks. In this situation, you can imagine the challenge posed by the situation of someone coming along and taking one of those drinks off the tray. Assuming that the waiter sees the person starting to reach for the drink, a forward model would be involved in predicting the consequences of the drink being removed. The forward model is about making the predictions about the expected consequences of the perturbation. Let's look at a study by Shadmir and Musaravoldi that's investigated the idea of internal models. The hypothesis driving this research is that the central nervous system has an inverse model of limb dynamics, and that model is used for controlling reaching. Recall, inverse dynamics is the transformation where if I'm given a particular trajectory of, let's say, the hand through space, I work out what kinetics, what forces, what torques are needed to produce that movement through space. The hypothesis, then, is that the central nervous system is organized to seemingly contain a model that transforms the intended movement trajectory into a pattern of torques. Participants in this research performed a simple task. They simply had to move a cursor towards a target. The cursor appeared on the monitor, and they moved the cursor by moving a handle attached to a robotic arm through space. Here we can see what the participants saw on the screen. The participant-controlled cursor is the right square on the screen here, and the task here is to move the handle that you're holding so that the cursor moves towards the target, which is the black square. The most significant part of this research is the robot arm. The researchers use this robot arm to change the forces that are required in order to move the handle. Torque motors in the robot arm are used to create particular force fields. Here we see an example of one of the force fields that's studied in this research. The force field determines the forces that the participant has to exert in order to move the cursor. The arrows in this picture show the pattern of resistance that the participant experiences at a particular location in space. So, over here we see the position of the cursor, and here we see one of the particular targets. In this experiment, we're going to be looking at multiple target directions coming out here. So, when the participant is at this particular position here, we can see these arrows representing the forces that they're going to be experiencing. When they're holding the handle, this handle is going to be pushing on them to push them in this direction. So in order to hold this handle still, they're going to have to pull in this direction. They're going to have to pull towards themselves, and they're going to have to pull towards the left a little bit. So when we look at A and B, we can see different locations in the force field, and at each of these locations we're going to be experiencing different pulls on the handle. If you're at point A, the robot arm is going to create a force that's going to pull away from you and towards the right. If you don't resist the pull, your hand is going to be moved. If you're at point B, then the force field will be acting to try and pull you to the right. An important aspect of this study is that no instructions are given about what trajectory should be used to get to the target. The reason for this is that we don't want to bias how people do the task. In theory, there's no bias about how you should actually perform this movement then. I could be starting off here, and I could take a straight line movement to get myself to the target, or I could be taking a completely wiggly motion to get to the target. In both cases, based upon the instructions, I would be doing the experiment as asked. In order to understand the key takeaway messages of this research, we're going to focus on the conditions in this research where participants are asked to move to the target location without using visual feedback. The way the experiment works in this condition is that the participant can see the cursor before the trial starts. They can also move around the cursor, but as soon as the instruction to begin the trial occurs, the participant starts to move and the cursor immediately disappears from view. So at the beginning of the trial, I can control the handle, I can be moving the cursor around, but then when the trial begins and I start to move towards the target, this cursor is going to be hidden from view. So why are we doing this? If participants have visual feedback of cursor position as they move, then they will be seeing how the force field is pushing them, is going to be pushing them around. Let's look at what happens when people actually do this experiment. Here we have a plot of a number of movements that are occurring in the first few trials of doing this task. These are trials in the experiment where no force field is being applied. This means that the robot arm isn't pushing on the handle in any way, that your hand isn't being influenced by the force field in any way. You can see that we get pretty much straight line trajectories from the initial cursor position in the center of the screen out towards the 8 target locations investigated around the periphery. So what happens when we have a force field being applied to the handle in the first few trials? What do we end up seeing? If you look at the pattern of force that the force field is applying to the handle over here on the left, you can get a feel for how the handle and the hand is being pushed around as it attempts to move towards the target. So, for example, on this trajectory here, we can see this is the direction of the force field acting here, and the hand is being pushed away from the straight line trajectory here. If we look at the trajectory that that's labelled A here, that we were just talking about, we can see that the force field is initially acting to pull the handle away from the participant before they correct the disturbance and then pull the handle back. So people are still knowing how to get to the target, but the force field is pushing them away from having a straight line path. To try and understand the results that are being seen in this study, the authors created a simulation of the movement pattern that should be expected to have occurred in the situation where a straight line movement in the no force field environment is planned, but that planned movement gets executed in the force field environment. So they're going to create a simulation where they're assuming that what's being planned is to do a straight line movement, and that movement is actually going to get executed in the force field environment. Based upon this assumption, we see the output of the simulation here. The simulation produces the same characteristic curves that were produced by the participants. The similarity between the simulation and the actual participant performances suggests that the initial movements aren't actually adapted to the force field in any particular way. The authors suggest that the similarities between the simulated and the actual trajectories is suggesting that what participants are doing when they first experience the force field is utilizing a pre-existing model of the forces that should be affecting how their arms move. We just looked at what happens when the participants first experience the force field. Let's now look at what happens in this experiment after a few trials have been completed. There are 2 different phases that we're going to look at. In phase 1, we're going to look at how participants move to the target location over multiple trials performed in the force field environment. And in phase 2, we're going to look at how participants move to the target location after the force field was turned off. Let's begin by looking at phase 1. What did participants reaching movements look like across multiple trials within the force field environment? So, we're going to look at some participant performances averaged over trials. The plot on the top left shows the average trajectory for the first 250 trials. Even though we're looking at the average trajectory over 250 trials, we can still see the characteristic curves that were predicted in the simulation. The other 3 plots show the average data for the second 250 trials, the third 250 trials, and the final 4th set of 250 trials. By the end of doing hundreds and hundreds of trials in this pretty insane experiment, the curvy trajectories have started to become straight line trajectories. So what's this data revealing to us? Remember, participants don't have visual feedback here, and so they're not seeing how their arm is moving. Even so, we're seeing the trajectories becoming smooth and straight with practice. And again, remember that there are no instructions given about what kind of trajectory was okay or preferred. Nevertheless, all of the participants ended up adapting over time towards having these straight line trajectories. So, over multiple trials, we see that the trajectories are becoming smooth and straight. the trajectories end up looking like typical reaching movements in free space, and they end up looking like the straight line trajectories we saw in the no force field experiment, the no force field environment. So, how do the authors interpret these findings? The internal control system, according to the authors, is gradually, over hundreds of trials, reorganizing itself. Specifically, there's an inverse dynamics model in the control system that's being slowly updated. This model takes in the information about the position of the arm, and it outputs the torques that should be generated in order to hold the arm in that position and to move the arm through space. In other words, these results suggest that there is a model inside the nervous system that's learning the kinds of forces and torques that are needed in order to move the arm through space. Applying this data to a real-world context, you might imagine that you're wading through a lake, with your legs moving through water rather than through air. The water is going to resist your movements in a particular way. If you're moving your legs through the water for an extended period of time, you're going to relearn the types of forces and torques that are needed in order to move your legs through the environment. And that's the kind of learning that's happening here. This is a long timescale learning process. It's a very slow process, but people through that process are learning a new mapping between a change in position and the torques required to make that change in position. In other words, they're learning an inverse dynamics transformation. So that's what happens in phase 1 of the experiment. In phase 2 of the experiment, we're going to take the participants that have been through these hundreds of trials in phase 1, and then we're going to turn off the force field. At this point in the experiment, we've just experienced 1,000 trials of performing these different reaching movements with the force field turned on, and now it's going to get turned off. Here we have the average performances for reaching to targets in the no force field environment. What are we seeing here? We end up seeing that people reaching to the targets with no force field on are doing so using curved paths. These results look like the data from the first 250 trials from phase 1. So we can see the same characteristic trials from the first 250 trials in phase 1, and those characteristic curves are existing again in the first 250 trials in phase 2. What you should notice is that they look similar, but they're mirror images of each other. It's clear from these results that after moving in the force field environment for such a long time, the participants have learnt a new way of controlling their movements in the environment. What we're seeing is that over the course of the experiment, people have learnt a new mapping between forces and movements, and that when the force field is removed, they continue to apply that mapping. What we're seeing here is that participants are no longer adapted to the no force field environment in the same way they were when they began phase 1. What's happened here during this experiment is that we've retrained the nervous system to understand what it means to move their hand through space in a new way. In the next part of today's lecture, I want to take you through 2 distinct approaches to understanding how targeted arm movements are organized. One idea is that targeted arm movements are organized in terms of a particular distance to the target being programmed. Another idea is that targeted arm movements are organized around programming a particular location in the environment. So, what does it mean to organize a targeted arm movement by distance programming? It means that initially we have a subject who can visually perceive the distance that the hand needs to cover in order to get to their hand to the target. And next it means, based upon visually perceiving that distance, that the subject can activate a set of agonist muscles to propel the arm the proper distance to the target. Then, once the arm has been propelled through, towards the target, a set of antagonist muscles can be activated to provide the braking force necessary to arrest the motion. In simple terms, you visually perceive the distance to be reached, and then you program the torques that will be necessary to propel the hand that distance through space. The alternative to distance programming is location programming. With location programming, we have the idea that the central nervous system is going to program a balance of tensions between two opposing muscle sets in order to get the hand to move to a particular location in space. Now, this idea might be a little bit unclear at the moment. If it's unclear, don't worry about that too much, since we're going to be carefully unfolding this idea in detail in a couple of slides' time. In the location programming theory, every location in space is going to correspond to a particular family of stiffness relationships between opposing muscles. We're going to set a relative stiffness between agonist and antagonists, and based upon that stiffness relationship, the hand is going to move to where those two stiffnesses are going to balance out. Let's start by looking at a couple of different theories that are consistent with the notion of distance programming, that are consistent with the idea that what's programmed by the central nervous system during arm movements are the muscle activations or the torques that are necessary to move a hand a particular distance and direction through space. The first model that we're going to look at in this category is the impulse variability model. To set the stage for understanding this model, here we have a person who's looking at a coffee cup with the intention of reaching towards it. The limb movement here is going to result from muscular torques being applied at the joints, and the hand moving a particular distance and direction through space as a consequence of programming these torques. So why is this called the impulse variability model? Impulse, if you remember from biomechanics class, is equal to force multiplied by time. It captures how forces are going to act over time. Impulse is going to be a critical determinant of the distance and direction that the end effector travels. So if I apply a torque at the shoulder and at the elbow, I can move the arm and I can move the hand through space. How much torque I apply and how long I apply that torque for will determine the distance and direction that the hand is going to move through space. Schmidt provided some evidence in support of this particular way of thinking about how the nervous system organizes performances of reaching. He investigated the task of making a fast movement aimed at a target a fixed distance away. What he found was consistent with the idea of impulse or torque-based control. He found that targeting error, that is, the amount of overshoot or undershoot that you would see in terms of reaching for a cup, changed in proportion to the magnitude of the force that was used at the joints. So, when you look across different reaches of the hand towards a target, you see the variability of forces and torques at the individual joints are closely related to the variability in terms of the accuracy of the reach itself. For Schmidt, this meant that there's a direct relationship between joint torques and reach accuracy. In sum, what we have here is some evidence that suggests that reaching movements can be organized by programming the torques needed to move the hand a particular distance and direction through space. Let's look at another distance programming theory. In this theory, we have the idea that movement trajectories are corrected based upon visual feedback. In this graph here, we're looking at reaching movements of the hand. We have the velocity of the movement on the y-axis, and on the x-axis we have the distance between the hand and the target that the person is reaching towards. The target area, shown with the red lines here, that outlines the particular location that the participant is reaching towards. The three black lines on the graph are for different reach trajectories. What we're looking at here is open loop control trajectories. Open loop control means that I generate some joint torques that throw my hand towards the target. Sometimes the movement plan is going to be perfect and the hand will be launched in just the right way so that it lands exactly on the target. Other times the program talks will not be perfect and the target might be overshot or undershot. So we have an open loop control which is going to throw the arm towards the target. And then after that we have a closed loop control process that's going to act to correct for these overshoots or undershoots. The combination of open loop processes to propel the hand to the target and closed loop processes to correct errors in the open loop process is going to form the basic idea of the visual correction theory. This is a distance programming theory because you're initially programming a distance to throw the hand towards the target. Let's look at some research that's motivated the visual correction theory of reaching. Here we've got a simple task that was studied by Woodworth. In this task you have to move a stylus backwards and forwards between two targets in time to a metronome. And here we see the results of this research. On the y-axis we have targeting error. 0 error on the y-axis means that the stylus is landing exactly in the middle of the targets, and 5 on the y-axis means that there is either an overshoot or an undershoot of 5 millimeters. So we've got millimeters as our units here. So we're looking at very accurate reaches here. 5 millimeters is less than 1/4 of an inch. On the x-axis we have movement velocity, ranging from 5 centimeters per second to 50 centimeters per second. Woodworth manipulated the speed of the movements by changing the speed of the metronome. Remember, the task was to move the stylus backwards and forwards in time to the metronome. When the metronome is beating faster, you have to move faster backwards and forwards between the two targets. Let's start by focusing on the eyes closed data, shown with the dashed line. This data is for the task of initially looking at the targets, before then closing your eyes and then moving the stylus back and forwards between the two targets in time to the metronome. The initially surprising thing to realize is that the task can be done quite accurately with eyes closed. The next thing to notice is that eyes closed reaching accuracy does not seem to change with movement speed. Now, when we look at the eyes open data, we see very different things going on. We see very different results. When the movements are slow, the targeting error is dramatically reduced. So, when you have slow movements, you're able to visually perceive your targeting errors, and you're able to provide some kind of correction to reduce your error. When the movement task is performed more quickly, the benefits of vision quickly disappear. As soon as the hand is moving at around about 25 centimeters per second or faster, there is not a noticeable difference in the accuracy between eyes open and eyes closed performance. The lesson here is that vision is improving targeting performance, but only when movements are slow enough to allow visual feedback to be processed. In case you didn't notice, I've just described some very, very old research. This study was performed in 1899. Now, I want to mention the findings of some more recent experiments that has helped us more precisely understand Woodworth's results, and that use a very similar paradigm to Woodworth. Keeler and Posner conducted a version of Woodworth's experiment using more precise measurement techniques. Their research revealed that aiming accuracy is affected by the presence or absence of visual feedback only when movements take more than around 200 milliseconds. Carlton similarly showed that you need to see your hands for more than 135 milliseconds during a movement in order for vision to be able to improve targeting accuracy. In sum, these results are consistent with the idea that reaching involves a feed-forward process where we're throwing our hands towards a target, and then a feedback process where vision is correcting reaching errors. What we saw here is that error can only be corrected if you have enough time to process the visual information about that error. As Carlton demonstrated, you need at least 135 milliseconds where you're able to see the movement in order to actually have any improvement of accuracy from vision. We've been talking about distance programming theories. Now let's move on to talking about location programming theories. Here we have a monkey in a laboratory experiment. The monkey has been trained to point its arm towards whatever light is lit up in front of it. So when the target lights up, the monkey is trained to move its arm so that its forearm is pointing towards the target. There are some specific things to note in this experimental setup. We have a baffle here, which means that the monkey is unable to see its arm. This means that arm movements will not be aided by visual feedback. The movements are also going to be performed without limb proprioception. The researchers have severed the dorsal root of the spinal cord in this monkey, and this procedure is effectively removing the capacity to haptically perceive the orientation of the limb. We're going to look at the pointing actions of the monkey that occur when the arm is either perturbed or unperturbed. When it's unperturbed, we're not actually going to do anything. But when it's perturbed, just before the reaching motion takes place, we're going to move the arm to a slightly different position. So, the way this experiment's going to work is that the light is going to come on, and then the experimenter is going to quickly move the forearm so that it has a different aiming direction just before the monkey's movement starts. So, remember, we've got no limb proprioception here. This is like doing this experiment to Ian Waterman. There's going to be no awareness in the monkey that its arm orientation has changed. Okay, let's look at the results of this experiment. In the middle of this figure, we can see thin black lines that show the change in forearm aiming angle over time. The red dotted line marks the initial posture of the arm, and the purple dashed line marks the target direction. On the right, we've got the unperturbed condition. We see that the arm starts on the red dotted line in the initial posture. The light then comes on, and the arm moves to point towards the target. On the left-hand side, we have the perturbed condition. The light comes on, the arm is quickly moved to a different position, and then we see the intentional arm movement start, and the monkey moves the arm to the target direction. This is a pretty surprising result. Even though the monkey is not aware of the change in position of its arm, it's still reliably pointing towards the target. Even though we've perturbed it and it can't perceive that change, the monkey is moving its arm to the target direction. This result sharply contradicts the distance programming theory. From the distance programming theory perspective, we're going to program a particular direction and magnitude of movement. Distance programming theory predicts that the monkey would program the arm to move, let's say, 25 degrees to the left of its initial position. It predicts that the movement would be programmed in terms of setting torques at the joints that would be needed to move the arm 25 degrees to the left. If I move the arm from a distance programming theory perspective, then I would expect to see those same torques would be used after the perturbation. We would therefore predict that the arm would not move far enough to reach the target. Contrary to the predictions of distance programming theory, aiming behavior is unaffected by the perturbation. It does not matter how the arm is moved. When the plan to act is executed, that plan does not care about where the arm was positioned before the reach. So, what does this mean? The implication here is that the pointing action is programmed as a goal location rather than a goal distance in this particular case. To recap, if the monkey had applied a programmed force or torque to move the arm to a desired position, then it would have missed the target. So, if we haven't got a force or torque being programmed, how is it that the central nervous system is specifying a pointing direction here? So, how can the central nervous system specify pointing direction in terms of location rather than direction? We're finally coming back to the slightly confusing statement I made earlier, and we're going to unpack it now. One theory of location programming is that location is programmed by setting extensor and flexor stiffnesses. If you set your flexors to have a particular stiffness, and you set your extensors to have a particular stiffness, then the balance of those two stiffnesses is going to lead the arm to be pointing in a particular direction. A simple way to understand this is referred to as the cafe door model of aiming. Here we have a swinging door. Think of when you're in a restaurant and you see the waiters coming through the door and the door being pushed open forwards and then bouncing backwards and forwards and then coming to a rest. One of the things about this door is that it can go either way. If we were to imagine taking the springs that exist either side of this door and then changing their stiffnesses, we would end up changing the position that the door rests at. So if I made K1 here, which is the stiffness of this spring much stronger, then we would see the door changing its resting position. So if I took K1 and made this a much stiffer spring, the door would rest pointing up in a direction, something like this. In the picture here, spring stiffness K1 and spring stiffness K2 are equal to each other, and so the resting position of the cafe door is going to be where it's shown here. If I move the cafe door to a new position, I have done something like moving the arm of the monkey. When I let the door go, it will automatically go back to where it started. By virtue of setting the balance of stiffnesses between these two springs, or the stiffnesses of the extensors and flexor muscles, the cafe door is going to always move itself back to the exact same original position. So here we see length-tension relationships for extensors in green and length-tension relationship for flexors in dark blue. On the y-axis, we have the joint angle that's associated with the length of the muscles and on the y-axis we have the tension in the muscle. If you remember back to biomechanics class, the slope of the length-tension relationship tells you the stiffness of the muscles. By setting the stiffness for the extensors and the stiffness for the flexors, the arm will move to a joint angle where the tension generated by these two muscle groups is in balance. So in terms of understanding the ability of the monkey to point at the target, the idea here is that the monkey is going to set the stiffness of the extensor muscles and the stiffness of the flexor muscles in such a way that the arm is going to come to a resting position in the new location prescribed by the change in stiffnesses. The idea here is that a joint position can be uniquely and equifinally specified via the setting of stiffnesses. I've used the term equifinal before. It refers to the fact that when I set these stiffnesses, I've programmed a location. You can perturb the limbs all day long. You can start from any location you want, but the result is going to be equally the same. The arm will always move to the same final location. So here we have a location-based theory of pointing. Now, there's two addendums that I want to add to the information that we have here. The first is that the results that we've got here have been effectively replicated in human pointing, suggesting that the insights of location-based programming apply just as well to humans as they do to monkeys. The second caveat that I want to discuss is that equifinality that we see in this pointing ability has some limits to it. If you allow both the shoulders and the elbow to vary in the perturbation that you make, the ability to invariably get to the target location ends up falling apart to some degree. So, we've looked at distance programming theories, and we've looked at location-based and location programming theories. The take-home message here is that there's evidence for both distance programming and location programming, and we don't have evidence that one particular way of programming movement is exactly how it's done. We were just looking at the question of whether targeted arm movements are organized in terms of distance programming or location programming. Let's move on to another dimension of how targeted arm movements are organized. When thinking about how a targeted arm movement could be organized, the movement could be planned in terms of limb kinematics, that is in terms of the arm's particular profile of movement through space, or it could be planned in terms of limb kinetics, that is in terms of the particular forces or torques that are being exerted. So let's have a look at some research that suggests that our movements are planned in terms of kinematics. In this experiment, we have some LEDs that are going to light up in front of you. In the actual experiment, there were little wooden dowels poking out that positioned the LEDs in space. On any given trial, 2 LEDs are going to light up, and your task is to start by pointing at one LED, and then you move your finger through space to be pointing at the other LED. So whenever 2 LEDs appeared and lit up in front of you, your task was to move your fingers from one LED to the other. Here we see the different LED targets. Each of the small red dots is one of the targets that were used, and the blue lines connecting the red dots show the pairs of targets that participants were asked to move between. One important thing to note is that each of these different target pairs have different distances between them. So here's some of the data. The data is looking at the tangential velocity of the wrist during various trials of pointing from one target to another. On the y-axis we have the tangential velocity, and on the x-axis we have time. We see that the velocity of the wrist increases, reaches a peak, and then comes down on the other side. When we look at the data for the different trials, we see that some movements took longer than others. We also see that some movements were much faster than others and had much greater peak velocities. To better understand these results, we need to time normalize and amplitude normalize this data. We've discussed normalization procedures before, and we've been doing normalization procedures throughout the semester in a number of ways. The most repeated way that we previously looked at normalized data is when we've looked at the gait cycle. We've looked at data that was normalized to the event duration of the gait cycle, starting from right heel strike and ending in right heel strike. Here what we're going to do is normalize the velocity profile. First we're going to align the peaks, and we take the moments of peak tangential velocity for all of the different trajectories, and we're going to line them up. And the next thing we're going to do is rescale the time axis. We're going to take the short duration movements and stretch them, and the long duration movements and compress them. Now, when we do this, we see something quite elegant. We find that all of these trajectories have the same pattern. When we rescale these trajectories, they pretty much all fall on top of each other, so that even though on different trials the reaches take more or less time, are slower or faster, or are reaching between different pairs of targets, they have the same characteristic across these different trials. To reinforce this point, let's have a look at the effect of some of the different manipulations of in this reaching task. On the top left, we have the data for participants performing the reaching movements at a slow speed, a medium speed, and a fast speed. When these different trials are normalized, we see that the profiles all fall on top of each other. You'll notice that we've got 2 sets of profiles here, one set above the line and one set below the line. These represent the different directions of movement between the targets in a pair. One direction of movement has positive velocities, and the other direction of movement has negative velocities. For example, if I start here and move up here, if I start here and move up here, it would have a positive velocity, but if I start here and then move down here, it would have a negative velocity. You'll notice here that the bottom set of curves are almost a perfect mirror image of the top set of curves. The curves on the top right, up here, show the effect, or lack thereof, of varying the mass of hand weights that were held during the pointing motions. If we didn't normalize this data, we would see different looking movements, but when we normalize them, we see that the underlying pattern is identical. In the bottom 2 graphs, we see the same story for changes in which particular target pair we're looking at and which particular subject that we're looking at. In summary, what we're seeing here is that movement kinematics have a clearly visible invariant characteristic to them. Remember, the concept of invariant characteristic was introduced when we were talking about the generalized motor program theory earlier. The invariant characteristic is the aspect of movement that is unchanged across many different variations of the movement. Here, the kinematic profile is invariant. The movement parameters here would be things like movement speed and the different torques related to carrying different hand weights. The conclusion drawn by the authors of this study is that the nervous system seems to be organized with respect to kinematic variables. Let's look at another conceptual distinction that's relevant to understanding the way in which targeted arm movements are organized. Are our arm movements planned in hand space, or are they planned in joint space? Movements planned in hand space are defined in the extrinsic coordinates of the external environment. This means that if I have a hand space plan, I'm going to plan a movement in the external environment. I'm going to plan to make a movement that moves my finger from one location in the environment to another. Here, we've got a straight line path of the hand through space. The logic that's used in this particular subliterature is that the simplest type of trajectory is going to be a straight line trajectory. Therefore, if you're planning a movement in hand space, you would expect to see hand movements that have a straight line path. If you have a straight line path in hand space, what are the corresponding joint space paths? Here we have the movement trajectory in joint space that is associated with a straight line hand space trajectory. Here we have, let's say, the shoulder axis on the shoulder angle on the x-axis and the elbow angle on the y-axis. As we see here, to produce a straight line path through hand space, we need a curved path through joint space. We have a simple straight line path in hand space, and we have a more complex path in joint space. Some researchers believe that straight line path hand trajectories are evidence that movements are planned in hand space rather than joint space. So, what's the alternative? Movements planned in joint space will use the intrinsic coordinates of the body rather than the extrinsic coordinates of the environment. If movements are planned in joint space, we would expect to see a combination of elbow and shoulder angles that produce a straight line in joint space. If we have a straight line path in joint space, we will get a curved motion path in hand space. So, why do we care about whether movements are planned in hand space or joint space? In other words, what are the pros and cons related to the nervous system organizing movements in hand space versus joint space? In theory, hand space plans require the computationally demanding inverse kinematic transformation. In order to plan this straight line movement through hand space, I have to do an inverse kinematics transformation. I have to work out what changes in the shoulder angle and elbow angle are needed to produce this particular trajectory. The reason that we have to perform this transformation is that we need to calculate joint angles in order to calculate the joint torques and muscle activations that are required. So to actually organize the movement, we have to use these computationally demanding transformations. In theory, joint space plans don't require this kind of inverse kinematic transformation. Because you're organizing your movements in terms of changes in angles of the joints, you don't have to compute joint angles. There's a downside for having movements planned in joint space. Movements planned in joint space are error-prone when trying to organize movements of the hand relative to the environment. Take, for example, the task of reaching to grab hold of the handle of a hot cup of coffee. What matters most in this movement is reliably and precisely getting the hand to the location of the cup in space. If we plan this movement in joint space rather than in hand space, then your ability to accurately position your hand relative to the handle of the cup is likely to be reduced. Let's look at some evidence that suggests that some arm movements are planned in hand space. Here we see a person holding onto a joystick. They are tasked with making reaching motions between the various targets shown. Here we see the trajectories that are produced. You will notice that we've got straight line trajectories. We see some curvature in one or two trajectories, but more often than not, these trajectories end up being straight. Here we're seeing trajectories that are simple in hand space. When we look at the joint trajectories, we see that they're not simple. The patterns of motion are complex in joint space. This is interpreted by these authors and others to be evidence that movements are planned in hand space. Now let's look at some other evidence in the literature that contrastingly suggests that some arm movements are planned in joint space rather than hand space. Hollaback demonstrated that almost straight line paths can result from relatively simple joint control strategies. Hollaback proposes a simple strategy. If you plan simple movements for each joint, but you vary the onset times of the motion of these different joints, so they're starting moving at different times, but they all stop moving at the same time, then you'll end up with a hand trajectory that has a closed straight line path. And you'll end up with a hand trajectory that tends to have just a little bit of curvature to it. The little bit of curvature is very interesting because this is one of the characteristics of reaches that we saw on the previous slide. Let's look at some more evidence that suggests that some arm movements are planned in joint space. Here we have some research by Buchanan, Kelso, and Diggersman. The research participants are asked to rhythmically trace a displayed trajectory with their hand. The target hand path is displayed on a computer screen, and your job as the participant is to rhythmically move your hand backwards and forwards along this particular path. A metronome is creating a beat, and so your job is also to move your hand along the path with this particular beat. The goal of this study is to understand the relationship that exists between the coordination patterns of joint movement and the path of the hand through space. To create the target pattern of hand movement, we need different patterns of joint angles to be coming together in order to produce this particular movement pattern. Let's take a look at some data from this study. On the graph on the left, up here, we see the trajectory of the participant's hand through space. On the right, we see the motions of the shoulder, the elbow, and the wrist that are coming together to create the movements of the hand. The dotted line here is the elbow angle, and the dashed line is the wrist angle. The black solid line is going to be the shoulder angle. When we look at this data, we see something quite striking. We see that the motion of the elbow joint is coordinated with the motion of the wrist joint. We see a one-to-one coordination pattern. This movement is organized so that the elbow and the wrist are almost perfectly coordinated. As the elbow is extending, the wrist is extending. As the elbow is flexing, the wrist is flexing. These two joints are organized to move together. What's this suggesting? This is suggesting that the motion of the hand through space is produced by organizing particular patterns of coordination between the different joints. Let's look at a different hand trajectory. So here we have a different hand trajectory here, and here we have the wrist, elbow, and shoulder motions that are associated with it. The hand trajectory that we've got here is much flatter than the first hand trajectory that was much more curved. Let's look and focus in on the joint motion data again. Here we have the elbow and the wrist. Again, we see these two joints are very strongly coordinated, but this time the pattern of coordination is different. This time when the elbow is flexing, the wrist is extending, and when the wrist is flexing, the elbow is extending. What we're seeing here is that the two joints are out of phase coordinated rather than in phase coordinated. What we're seeing here is that the joints are still organized to be coordinated, but in order to produce the new desired hand trajectory, a different pattern of coordination is used. There's another pattern to see in this data. If we look closely at the movements of the shoulder, we can see that the shoulder is also coordinated with both the wrist and the elbow. The shoulder is coordinated with the wrist and the elbow in an interesting and subtle way. For every 2 oscillations of the shoulder, we get 1 oscillation of the elbow. For every 2 oscillations of the shoulder, we get 1 oscillation of the wrist. So in both of these cases, we have 2-to-1 coordination. So what can we take away from these results? The hand motions in this study are produced by organizing simple patterns of interjoint coordination. These results suggest that when we see someone producing a particular trajectory of the hand through space, the organization that's sitting behind that movement is a particular coordinated pattern between the different joints. Another way to interpret these results is that different hand trajectories result from different coordination patterns, or to use a language we're more familiar with, different interjoint synergies. We've just been exploring the idea that our movements are planned in either hand space or joint space. Now I want to explore the idea that our movements are planned in task space. Bernstein studied professional blacksmiths striking a chisel with a hammer. The task here is to get the tip of the hammer to the tip of the chisel. To do this task well, the hammer needs to hit the end of the chisel both accurately and reliably. If this does not happen accurately and reliably, you're either going to break the object that you're working on, or you're going to squish your hand. Bernstein noticed that the details of each movement varied greatly strike to strike. From one strike of the hammer to the next, Bernstein observed that joint motions were combined in very different ways. On different strikes of the hammer, he saw different combinations of shoulder movement, elbow movement, and wrist movement. He also saw that the kinematic trajectory of the hand and the kinematic trajectory of the tip of the hammer through space also varied greatly strike to strike. In spite of this variability, Bernstein saw that each strike delivered a precise force to a precise location. Although the movements of the individual joints were very different strike to strike, the different motions of the joints always combined in a way to deliver the needed blow on the chisel, thus creating the needed amount of force at the required location. Even though there was strike-to-strike variation in the trajectory through space of the tip of the hammer, these varied paths of hammer motion reliably delivered the desired force at the desired location. What's the lesson to be learned here? The lesson is that highly skilled movements are organized around the goal of the movement, rather than the motions of the component degrees of freedom. We spent the last 10 to 15 slides discussing ideas and research findings concerning how targeted arm movements are organized. You'll be forgiven for being dissatisfied with what I've told you so far. Rather than showing you that targeted arm movements involve location programming but not distance programming, I showed you that both ideas are relevant. Rather than showing you that targeted arm movements are planned in hand space rather than joint space, I showed you evidence suggesting that both are true. I also showed you that sometimes movements are organized in joint space, but other times they're organized in task space. The reason that this is dissatisfying is that there's not one clear, straightforward answer. What we're learning here is that there's multiple ways in which movements are organized. You can understand this point by looking at research that has asked, what does the motor cortex control? The classical view of the functions of the motor cortex is that it's involved in the organization of muscle activations. The modern view of the function of the motor cortex is much more rich and complex. Contemporary research has shown that stimulation of various areas within the primary motor cortex are variously related to activations of muscle groups, the direction and velocity of the hand through space, joint angles, and types of actions in space. The lesson here is that there's varied forms of functional organization of movement in the nervous system. The systems approach provides a good framework for understanding the varied ways we've seen of organizing targeted arm movements. If we want to know why an action is organized in hand space, joint space, or task space, a reasonable answer can be found by examining the differences in the demands of the task and the constraints of the environment and the constraints of the individual that are shaping the way that the movement ends up being organized. We spent most of our time today exploring the idea that computational processes that are embodied in the functional organization of the brain act to organize functional movements. What I want to talk about for the next couple of slides is the idea that the spinal cord has an important role in the organization of functional movements. If I'm trying to understand the role of the spine, the question we want to ask here is what kind of role the spine and the spinal cord plays. Is the spine a simple receiver of commands, or is it a functional action system in its own right? Put another way, can we actually understand how functional movements are organized without incorporating the organization of the spine into our theory? The evidence over the next few slides that I'm going to present to you is going to suggest that we're going to need the spine in our story. The spinal cord does not simply relay signals from the brain to the muscles. Here we have a minimal schematic of the brain and the spinal cord. What we see depicted here is both horizontal and vertical neural connections among interneurons in the spinal cord. The research that I'll be showing you on the next couple of slides is consistent with the idea that the spine is a functional action system in its own right. If we take this to be the case, then the idea that the spine is just a passive recipient of messages relayed from the brain is not the best way to think about how the brain and the spinal cord are functionally organized to support functional movements. The modern theory of the function of the spinal cord is that instead of relaying commands, the brain is in the business of adjusting the geometry of the spinal cord organization. If we assume that the spinal cord has a rich organization to itself, then the role of the brain is to adjust or tune that functional organization, to tune the geometry of the organization. The idea here is that the spine is an autonomous movement system that is functionally adapted to the physics of muscles and the skeleton. Let's look at some research that supports the idea that the spine is a functional action system in its own right. Some of the strongest evidence supporting this idea comes from the study of frogs. Here we have a spinal frog. A spinal frog is a frog that's been surgically altered such that its spinal cord is isolated from the rest of its nervous system. In simple terms, the movements that are produced by the spinal frog are produced without the contribution from its brain. If an irritating stimulus is placed on the back of the spinal frog, it will perform a coordinated and precise wiping reflex in order to remove that irritating stimuli. In the diagram here, the irritating stimulus is depicted with a purple circle on the frog's back, and the dashed line shows the trajectory of the foot that's taken in order for the foot to wipe the irritating stimulus away. Oftentimes, this is achieved with a mildly irritating weak acid that just feels uncomfortable on the skin on the back of the frog. Given that we're talking about a spinal frog, it's very tempting to assume that the wiping reflex that we're seeing here is a mindless response, that it's an inflexible stereotype movement that involves the activation of specific muscles in a specific order. Interestingly, this turns out not to be the case. The wiping reflex is not a stereotyped activation of specific muscles. Instead, it's a functional movement that can be adaptively realized in multiple ways. So here we have our spinal frog again, in the smaller picture. What we see if we put the irritating stimulus on the frog's back multiple times is that sometimes the movement might be organized to create this overhand wiping reflex, such that the end of the foot ends up brushing off the irritating stimulus. Other times, we end up seeing a completely different movement being organized, such that the heel is moved to the stimulus to brush it away. So, we've got the spinal cord being involved in this movement. But what are we seeing? What we're seeing here is that a variety of functional adaptations occurring in the movement in order to produce the same functional result through different movements. To use the term that we've used a few times now through this class, the movements are equifinal. You get the same final result by multiple functionally equivalent means. There's some more we can learn by looking at the wiping reflex of the spinal frog. The wiping reflex of the spinal frog has been shown to adapt to the demands of the current situation to ensure that a functional movement is reliably performed. At the end of today's lecture, I'm going to propose that what we've just said here is actually a pretty good definition of what we mean by functionality. I will be proposing that a functional movement is a movement that's effectively adapted to the context in which it's performed. Let's look at how this idea plays out with the wiping reflex of the spinal frog. So, here we have our spinal frog again. As before, we're going to place the irritating stimulus on its back. This time, though, we're going to attach a large weight, for the frog at least, to the limb of the frog. This weight will completely change the joint torques that are required to execute the movement. Nevertheless, the frog still manages to wipe the irritant away. The wiping movement is performed in a different way, but the function is still realized. Let's look at another example. This time we're going to place the irritating stimulus on the frog's heel. The frog on the left in this image shows the basic reaction. The frog brings the two heels together so that one heel can wipe the irritating stimulus off of the other. For the frog on the right, we change things up a bit. This time we place an obstacle in its way. If the frog attempts to move in the same way that it just did without the obstacle in the way, the foot will just push into the obstacle. In contrast, what we actually see is that the frog moves its limb around the obstacle, and then proceeds to make contact with the other heel. From these experiments, we're seeing that even though there is no change in the irritating stimulus, and even though there's no change in any supraspinal process, such as a motor program, in spite of this, the neuromuscular degrees of freedom in the spinal cord are being adaptively reorganized to fit the demands of the situation. Remember, this is a spinal frog, so none of the concepts we've talked about today in terms of motor programs or higher-level planning are going to be taking place. The spinal cord is showing the potential to act as a standalone functional action system. The simple lesson of the spinal frog is that the spine is not trivialized when conceptualizing how functional movements become organized. Let's look at some research that gives us some insight into the role of the spinal cord in the organization of human movements. In this research, we're going to study performances of two simple tasks. Task 1 is to flex the hip, and task 2 is to extend the knee. The task is initiated by a go signal. After the go signal, there'll be a certain amount of time before we see the voluntary response. In task 1, we will have the go signal, and then this person will flex their hip. In the other task, we'll have the go signal, and then the person will extend their knee. In this experiment, the experimenters are going to give a tendon tap at various moments between the time of the go signal and the time of the onset of the movement. Gerfinkel discovered that if you provide a tendon tap very shortly after the go signal, then the expected reflexive response to the tendon tap will occur as normal. This was seen both for the flex the hip task and the extend the knee task. If alternatively the tendon tap is given shortly before the voluntary response, we find that the reflexive response did not unfold in the normal way that we would expect. Before we unpack this experiment further, I want you to be thinking back to the idea that we were talking about earlier. We have the idea that the function of the brain is not to send commands to the spinal cord. Rather, the function of the brain is to tune the kind of responses that are organized into the spinal cord. Let's look at how the reflexive responses are affected. And let's begin by looking at the results of the task of flexing the hip. When someone is intending to flex the hip, and a tendon tap is given, we see an increased response in the rectus femoris and an unchanged response in the vastus lateralis. The rectus femoris is a multi-joint muscle that spans both the knee and the hip joint. This muscle is involved in flexing the hip. So what we're seeing here then is that the intention to flex the hip is affecting the task-relevant organization of the spinal cord. Now let's look at the task of extending the knee. We're going to see the same results. Those muscles that are functionally involved in extending the knee are going to have different responses to the tendon tap. What we're seeing here is that the intention to perform these different tasks is tuning the organization of the spinal circuitry and is impacting the spinal reflexes we're invoking with the tendon tap. What's the take-home message here? The spinal cord is not a passive apparatus that's passively reproducing supraspinal instructions. Instead, it's a complex system where the interaction of the elements in that system is no less essential for motor control than the supraspinal impulses feeding into the motor neurons. In terms of understanding the particular results we've got here, we're seeing that the setting of an intention to perform a particular action is causing task-specific changes in the organization of reflexes existing at the spinal cord level. Put another way, task constraints are causing intention-specific changes in reflexes. I'd like to finish our discussion of normal motor control with a discussion of what constitutes functionality. So what is it that makes a particular movement functional and another movement less functional or dysfunctional? To get some insights into this question, I want to introduce you to some of the concepts that were developed by Nikolai Bernstein. For Bernstein, a person who is high-functioning has the ability to find an effective action solution to any emerging environmental situation. Rather than using the word high-functioning or low-functioning, Bernstein talked about dexterity. A dexterous person is a person who, when faced with a novel environmental situation, is able to adapt their movements to fit the demands of that situation. Dexterity is defined functionally. By this I mean that dexterity is defined in a way that accounts not just for the specific capacities of the individual, such as a person having greater strength. It's defined as the ability of a person to effectively organize actions that are adapted to the demands of the varied tasks and varied environments that they encounter. In other words, we're looking at a systems theory model of functionality. A dexterous person is going to be a person for whom effective action solutions reliably emerge across a wide set of variations in the constraints of the individual, the task, and the physical and social environment. The high-functioning or dexterous individual is an individual that can reliably find an effective action solution that reconciles all of these different constraints. For Bernstein, a key component of dexterity is the ability of a person to flexibly adapt their actions to the demands of the task to be performed and the environment that the task is to be performed within. The idea that we're exploring here is that functional movements are movements that are flexibly adapted to the context of constraints. A key component of this idea is that actions must be adapted to the environments in which they're performed. Put another way, dexterous actions are adapted to the environment of forces. What do we mean by this? we mean that the forces that are actively supplied through active muscle contractions are organized to complement the forces that are supplied passively. By actively supplied forces, we mean neuromuscular forces. And when we're talking about passively supplied forces, we're talking about the forces that result from the physics of the body interacting with the environment. This includes gravitational forces, inertial forces, and reactive forces. We looked at gravitational forces when we looked at the movements of the swing limb during the swing phase of the gait cycle. At the beginning of the swing phase, we saw that forces due to gravity acted to progress the swing limb forwards. We also saw that gravitational forces acted to decelerate the limb at the end of the swing phase. Inertial forces, if you remember, are the forces that result from Newton's first law, the law of inertia. When we looked at the swing phase of gait, the swing limb initially resisted being put into motion, but it was put into motion by gravitational forces. Once in motion, the swing limb has a tendency to stay in motion. This is due to inertia. This inertia keeps the limb in motion and carries the limb through mid-swing. We also saw that rotational inertia plays a role, and that part of controlling limb progression involved changing limb length through hip and knee flexion. This active control was used to modify the passively supplied forces of the rotational physics of the leg. Lastly, we have reactive forces. Whenever one limb segment is moving, that limb segment can apply forces to adjacent limb segments. So, with our gait example, the forward motion of the swing limb during mid and terminal stance creates forces that pull on the hip and act to pull the body forwards. The takeaway message here is that passive forces play a fundamental role in skilled action. When appropriately utilized by the skilled actor, passive forces make actions more efficient and more reliable. For Bernstein, dexterity requires that actions are organized in a way that accounts for the totality of forces. Here we see a schematic that simplistically represents what it means to produce the forces needed for a task. On the y-axis we have force, and on the x-axis we have time. The red line shows us the force that's required to perform the task. The blue line shows the forces that are potentially available from the physics of the body and the environment. So when I perform a particular movement, gravity is going to be acting. The various passive forces are going to be acting. All of those passive forces can provide a field of forces that can partially generate the force field that's desired. If I'm a highly skilled and efficient individual, the only active forces I should be bringing to bear to the task are those forces that are needed to transform the passive forces that I get for free into the force field that's desired. The skilled actor will quickly learn how to use the gravitational forces and reactive forces that they get given from the physics of a particular situation. The act of a baseball pitch is a nice intuitive example. In order to efficiently pitch the baseball, you want to take advantage of the forces that are flowing across the joints during the action, and utilize those forces to create an efficient transfer of energy from the body through to the ball. I want to finish today's lecture and our discussion of how functional movements are flexibly adapted to the context of constraints by looking at an experiment by Snyder. The task performed in this experiment is a simple one. As a participant, all you have to do is move your hand up and down between two targets and around the barrier that's shown as the green line. In the experiment, the participant holds a handle with a cylinder attached to it. The cylinder is shown with the blue circle. The task is to move the cylinder back and forth between laser beam A and laser beam B. So you have to start down here, break the laser beam, and bring the cylinder up until you've broke the laser beam here. So you start off by moving the cylinder to break the laser beam at A. You then move up and around the barrier to break the laser beam at B. So the task starts at A, From A, you move up and around the barrier, and you should note that this part of the movement is an anti-gravity movement, where you're working against gravity. You then have to break the laser beam at B, and from B, that you then move back down to A. Note, now what we've got is a with gravity movement, so gravity is pulling you down. And then finally, you're going to come to a rest at A. The experiment concludes when 100 successful trials have been performed. Let's look at what was found in this experiment. We're looking at this experiment because we're interested in how actions become adapted to the context of constraints. Given that participants perform 100 trials in this experiment, we're interested in the effect of practicing the task 100 times. 100 trials of practice resulted in substantial decreases in movement time. At the end of practice, participants could perform this task much more quickly. At the end of practice, the EMG profiles of primary muscles utilized in the task exhibited much less co-contraction. We also see that unnecessary wrist motions that were present when the participant first started performing the task were eliminated by the end of training. This suggests that the participants are learning to only produce those motions that are needed to support performing the task. Together with the evidence of reduced co-contraction, this suggests that participants are learning to perform the action more efficiently with less wasted efforts. Examination of the timing of muscle activation patterns by the authors indicated that practice was associated with learning to utilize the passive dynamic resources of the muscles. In other words, participants learned to exploit the viscoelastic properties of their muscles to increase movement efficiency. So, what do we mean by this? One of the examples that the authors cite is that by the end of practice, when the arm was approaching a reversal point, so either A or B, the biceps was active while lengthening. In other words, at the end of practice, participants were eccentrically contracting their bicep as the arm reached forward towards the laser beams. As the hand moves towards the reversal point, the biceps is lengthening in order to allow the hand to reach forwards. During this movement, the biceps is eccentrically activated. This creates a braking force from the biceps by virtue of its passive stretching coming towards the target. This force is going to control and reverse the motion of the hand towards the laser beam. The passive stretch of the biceps is then going to passively aid flexion using stored elastic energy. The lesson here is that the process of becoming more skilled at a task involves learning to utilize the resources that are available in the context that the movement is being performed within. So that wraps up our material on normal reach, grasp and manipulation, and on normal motor control. Okay, thanks guys, and